Going a little bit above the sea ice and the Arctic Ocean. Talking today about the near-surface profiles that we took over the snow-covered tundra and fjord water that we took back in a campaign in 2020. Hold on. No. Okay, can everyone still hear me okay? Okay. Yeah, so first I'd like to just start off by talking a little bit about the water cycle, specifically in the European Arctic. So you can have, under conditions, colder outbreak conditions, you can have cold, dry air coming over the sea ice edge, transporting south and encountering the warm ocean water in the Fram Strait, where there's intense moisture fluxes. That moisture is then transported south towards the Norwegian mainland, where it encounters the Norwegian topography, falls out in precipitation. So now one thing I'd like to mention is that not just specific to the European Arctic, but in general, the water cycle in numerical models can be subject to the representation in these numerical models can be subject to compensating errors between subgrid scale processes. So you can have overactive evaporation balanced by over-efficient precipitation. So you're arriving at the correct moisture content answer for the wrong reasons. And so, as many of us are familiar with, of course, when you're dealing with processes in the water cycle, you can use stable water isotopes to give information on these processes. So for my own part, I focus on evaporation and evaporation in the Arctic. Looking at the evaporative signal of stable water isotopes there. More specifically, looking at the question of what is the deuterium excess signal that we see in the Arctic, specifically during evaporation. The theory of Craig Gordon, which suggests that under these strong gradients in temperature and humidity that we encounter in the Arctic, we would have high E excess due to the strong kinetic fractionation occurring there. However, there have been some recent studies saying that the Arctic is actually an origin source of low E excess. So we thought to go there and make in situ measurements to shed light on this question. So that's exactly what we did during the ISE-CUBES 2020 campaign along the western coast of Svalbard, close to the Fram Strait. So here we are on the western coast of Svalbard. So in February, March of 2020, we went to Analyser, and zooming in on the settlement itself on the southern shore of Kongsfjorden. We made two deployment sites, one over the snow-covered tundra represented by the red circle, and the other just on beside the fjord represented by the green triangle. Sorry, I might have said red triangle, I meant red circle. Here's a different view of that from the Zeppelin Observatory of the two sites, and you can actually see on this particular day the intense Arctic sea smoke, the smoke on the water that is a visualization of sort of intense moisture fluxes that are going on in the conditions that we're sampling under. So actually Hans Christian had a great segue for myself in that these instruments that we use to make our measurements in the field are typically, they were born in the lab. So we need a way to actually make these in situ measurements in a low impact, low footprint kind of way. And so to do that, we developed a prototypical deployment platform that for our CRDS analyzer called the ISE-CUBES, which is essentially a Picaro analyzer in a temperature regulated portable container. It's quite mobile, and then accompanied with the necessary sorts of pumps and power supplies and other sampling equipment in the other boxes. So here are the ISE-CUBE stacks at the two locations. See my glasses, but so here's the ISE-CUBE stacks at the two locations alongside the profiling arm that actually enabled us to take these near surface profiles. Here you can see the profiles on the left at the snow in the uppermost position, and at the water at the fjord near its lowermost position, close to the surface of the water. So at the head of the arm, we had ultrasonic distance and temperature sensors to give information about the kind of, well, one, to get our profiles and to give information about what sort of isotopic signal we were sampling. We also collaborated and deployed next to the Nightfox campaign from the University of Bayreuth and the Alfred Wegener Institute in Potsdam, and that is high resolution temperature sensing columns. would have liked to talk more today, but I actually can't. So if you want to, we can discuss that afterwards. And then, of course, at both locations, we deployed next to ambient meteorological weather stations to give an indication of the kind of winds and temperature we had going on. Speaking of temperatures, it was abnormally cold for that time of year. So it definitely presented with a challenging testing ground for the ice cubes. Our winds were a little more typical, though we did have kind of two different regimes of these low winds below 3 meter, 4 meter per second, and then more elevated winds above 8 to 10. So now I'd like to show you some of the profiles from 2 days in particular, where we had very low winds below 3 meters per second, as well as very cold below -20 to -28 Celsius. From over the snow, the 28th of February, and over the fjord, the 10th of March, both having winds from the south or southeast. So that's represented in this little figure up here with the wind sourcing from. So we can see that over the fjord, which is the green triangle line, we can see warm, moist air the closer we are to the surface of the water, whereas at the snow, the closer we get to the snowpack, we get cold and dry. So now, interestingly, when we look at the specific humidity, the upper levels of both the snow and the fjord have comparable humidity levels. However, when we look at the isotopic profile, it actually tells quite a different story, that the deuterium over the snow was quite a bit more depleted than the upper levels of what we saw over at the fjord. Now, when we look at the deuterium excess, we see that near the surface of the fjord, we see high d-excess values decreasing as it mixes with the overlying air. And then at the snow, we see very low d-excess values as the snow is coming directly into contact with the snowpack. Moisture in the air is coming directly into contact with the snowpack. It's also important to note that during sampling at the snow, when we consider the relative humidity normalized to the surface temperature with respect to ice, we are basically always at saturation. So it was, we could actually see the deposition onto the surface of the snowpack in the form of frost flowers and hoarfrost while we were sampling over at the snow. So now looking at the d-excess profiles, we can kind of see two processes going on that are interacting with the overlying air. One is a production evaporation going on at the fjord, high d-excess. The other is a removal, a deposition process going on over the snow. But then, of course, this raises the question of if you were to take a singular, like a sample at any one particular level, what you actually get as a signal can be quite different depending on what height you're at and what kind of processes are going on around you. So now we can not only look at our measurements in a physical space of looking at the vertical profiles, we can also look at our isotopic measurements in humidity space. So if we look at the 5-minute average of all of our data from the two deployment sites, we can see in the log. So this is the x-axis is logarithmic humidity, and the y-axis is the delta D. We can see that there's kind of two sort of clusters going on. One more depleted over the snow, similar to that the red profile that we saw in the previous figures, and then another one that's more enriched over the fjord. And keen-eyed observers might see that one of these things is not like the other, which is actually what we measured when we were at the snow on the 25th of February. Which, interestingly enough, was the only day when we had strong winds coming from the northwest. So we had kind of a maritime signal affected over the snow. Then on the midnight going from 25th to the 26th, we had a 180-degree switch of winds to come from the southeast, and winds dying right down to 2 meters per second or less, and this gradual meandering from this maritime regime to the very depleted signal that we saw for the rest of the time at the snow. When we look at the d-excess, we can also see these very depleted values, but we also see the very enriched values that we saw when we were profiling over the fjord. On the 10th, I forgot to mention earlier, we was the closest we actually got to the surface of the water, about 30 centimeters or so. The other days were not quite as low. And the only time that we actually see humidities comparable to what we measured when we got so close to the surface were actually on days when we had stronger wind signals. So that is kind of showing that there's this mixing process going on between what's produced over the water mixing with the overlying air. So if we go back and we think about these two processes going on affecting the moisture, this again brings me back to my point of if you were to take a singular measurement at one point, what's your d-excess? That makes it particularly difficult to nail down the question of what is the d-excess signal of the Arctic. So to conclude, I'm not sure how I'm doing for time, but I hope I'm okay. I think my first conclusion would be to say we're very happy that we actually made these in situ profiles during Arctic winter. It was challenging deployment with particularly challenging global issues at the end of the campaign, but I think ultimately we were very happy with it, with our data set. And then to address the question of whether the Arctic is a source of high or low d-excess, I would actually argue that it's a false dichotomy, and it is actually both, because you have these processes going on that both generate high d-excess signal during evaporation, but then you also get this freeze drying that is really lowering the d-excess in the saturated conditions. So ultimately, if you take observations at any one level or any one point source, it doesn't tell the full story. So we really need to investigate these processes going on the vertical structure of these processes. So with that, I'd like to thank you for your attention and welcome any questions.